Muchas gracias, Laura. Un placer estar aquí. Muchas gracias también por la invitación, por todo. Lo que voy a presentar es el problema del flujo. Una cuestión que gustaría exponer es si puedo presentar en porque los términos técnicos no los sé ni en portugués ni en castellano. Para mí es un poco más fácil. Gracias. Okay, so this is a work that I did my PhD thesis some time ago on this topic. And then I developed the topic slowly, but recently in this year we published some papers that are more or less new results in the field. Before I present these three papers, I would like to do a brief review of the literature on the field, and you will see more or less that there are quite a lot of algorithms that could not solve the problem, because the problem is very difficult to understand. It was in the 80s and before. Now people understood that there are two kinds of solutions, and it was not obvious in the 70s and in the 80s. You remember? And so they tried to apply algorithms directly from the concepts of linear programming. So let me introduce this work was mainly done with my PhD student José. He will defend his thesis on 27, so in a few days. The contents of my talk is a very short introduction, then a brief survey of literature. And before the survey, I'd like to tell you that this problem is a very, very difficult one because the number of solutions is a huge number. And then linear multi-objective network flow problems, linear integer, multiple objective integer network flow problems, approximative algorithms for this kind of problems, and interactive procedures. There are quite a few. And the recent developments with this is a primal dual algorithm for the bi-objective network flow problem for linear case, and an epsilon constant algorithm for the b-objective integer network flow problem, and the zero-cost algorithm for computing all the supported solutions for multiple objective network flow problems. Then some conclusions and some more references. We have a network with two cost functions, C1 and C2, and the lower bound Lij, and the capacity Uij on each arc Rj. Okay? And the numerical value Pk associated with every node of the network. And then if Pk Pi is strictly greater than 0, it means that is a node that is a supply node, is a node that contains some product, for example, package of information, and would like to send this package to other nodes that are demand nodes. And if there are nodes where P is equal to 0, we call transshipment nodes. And then if I consider only the two criteria of two objective problems, we have two objective and linear objective functions and a set of feasible solutions. And this is the integer case, but the linear case, we know that the variables are in positive and in Rn, and then this is the conservation constants, and here the capacity constants on each R. And if we are the integer case, for example, they should be integer, and of course we put this greater than 0, then for us this Lij should be greater than 0. We can do different. A basic concept in multi-objective network flows and also linear programming and mathematical programming is the only concept is the concept of dominance. The others are derived from this concept. This concept allows to compare solution pairwise comparisons. And we have two sets, the dominated and the non-dominated. The other concepts are derived from this one. Okay, then so if we consider two solutions, two vectors, y prime and y double prime, these are feasible solutions in the objective space, and we will see what I mean by objective space and by decision space. Then y prime dominates y double prime if, in terms of vector, y prime is lower than or equal to y double prime, and they are different. It means that for each one of the criteria, we are minimizing, okay? Should be lower than or equal to the other solution for all criteria with at least one strict inequality. This is the definition. This fundamental concept, and from this fundamental concept we can now have the non-dominated solutions in the objective space. I will call non-dominated in the objective space, and efficient solutions in the decision variable space, in the space of flows, and the other is the space of the outcomes of the object. Okay? For integer problems, we have also supported and unsupported solutions, and this is important. Okay, let me see. This is an integer problem in the criterion for objective space, and we have a set of points. Some will be non-dominated and the other will be dominated. We have only two objectives, and now look, I'm using the definition of the negative cone because we are minimizing the two objectives, and then if we put this cone on each one of the solutions, there is nothing inside. It means that these solutions are non-dominated. But put this negative cone here, and you have a lot of solutions inside. They are better than the one we put the negative cone. Here it's not the case, so we know how to define these solutions. And then we have in the red, the color, the solutions. The main source for this brief survey of the literature was in this PhD thesis of Augusto on multi-objective network flow problems. Before this complexity, or more the cardinality of the set of non-derivative solutions, and Punta rule in 88 showed and taking into account the Zate graphs. Zate graphs were used for minimum cost network flows, for another kind of analysis. And we used this kind of graphs, add one more criterion, and he showed that a number of supported supported solutions are exponential in terms of the number of nodes. So the problem is very difficult because there are a huge number of solutions. And we know also that the number of supported solutions are very smaller when compared with the unsupported ones.